A meteorite that fell to Earth 300 years ago contains a material that breaks the normal rules of physics. When things get hot, they conduct heat differently. Crystalline structures get worse at it, while glassy, disordered structures get better. But a substance hidden inside this meteorite does neither. Its ability to conduct heat remains constant, whether it's freezing cold or scorching hot. For decades, this property remained a secret until an artificial intelligence finally revealed it.
This discovery, published in the Proceedings of the National Academy of Sciences, carries immense practical importance. It points toward a new class of materials for managing heat in the most demanding environments imaginable. Think of thermal shields for spacecraft, components for next-generation electronics, or even more efficient industrial processes here on Earth. The breakthrough came when researchers at Columbia University and collaborators in Europe used machine learning to solve the fundamental equations of quantum mechanics with unprecedented accuracy. This AI-driven approach allowed them to predict the existence of a material with these hybrid crystal glass thermal properties before it was even confirmed in the lab.
So, how did this incredible material hide in plain sight for so long? What exactly did the AI do that researchers couldn't before? And what does this discovery mean for building the next generation of technology for space and beyond? The story begins with a specific type of silica mineral called tridymite. It's a form of silicon dioxide, the main component of sand, but with a unique structure. Scientists in the 1960s had noted that this form of tridymite was typical in meteorites, but its strange properties were not fully understood. The specific sample that unlocked this mystery came from a meteorite that landed in Steinbach, Germany, way back in 1724. For centuries, it sat in a museum collection, a piece of cosmic history. This material is a time capsule, holding pristine matter from the early solar system.
Scientists have long studied meteorites, using powerful tools like electron microscopes and spectroscopy. They saw complex, jumbled atomic structures, but struggled to connect those structures to their physical properties. The sheer chaos of the atoms made traditional calculations impossibly complex. They had the raw data, but couldn't decipher the underlying rules. This created a major challenge, because controlling heat flow is critical for technology. In space, a satellite swings between the freezing cold of shadow and the intense heat of direct sunlight. Materials that expand and contract can ruin sensitive instruments like telescope mirrors. So we have a centuries-old meteorite containing a material with a chaotic structure and a critical need for materials that can handle extreme temperatures without changing their properties. To put this in perspective, the thermal expansion on a typical satellite can cause components to shift by several millimeters. For a precision instrument, a deviation of even a few nanometers can be catastrophic.
This is where the artificial intelligence came in. Researchers developed a machine learning model built on the fundamental principles of quantum mechanics. They trained this AI on a massive database containing the atomic structures and known thermal properties of thousands of different materials. The AI learned to recognize the subtle patterns connecting how atoms are arranged to how they conduct heat. It became incredibly good at predicting a material's thermal conductivity just by looking at its structure. Researchers then fed the AI the messy, complex structural data from the meteoric tridymite. The AI analyzed the atomic arrangement, which was neither a perfectly ordered crystal nor a completely disordered glass, but something in between. The model's stunning prediction was that this hybrid structure would have a thermal conductivity that remains almost perfectly constant across a huge range of temperatures. This behavior is analogous to the Invar effect, where some metal alloys show near-zero thermal expansion, a discovery that won the Nobel Prize in Physics in 1920.
To verify the AI's prediction, a team at Sorbonne University in Paris obtained permission from the National Museum of Natural History to perform experiments on the actual Steinbach meteorite sample. They carefully extracted a tiny piece of the tridymite. Their lab tests confirmed the AI's prediction with stunning accuracy. They found its thermal conductivity remained essentially constant over a temperature range from 80 Kelvin to 380 Kelvin. That's a range from colder than dry ice to hotter than boiling water, yet the material's thermal performance didn't change. One limitation, however, is that this material is only found in tiny quantities within meteorites. The next great challenge is to synthesize it in a lab.
This discovery fundamentally changes how we search for new materials. Instead of relying on slow, painstaking trial and error in a laboratory, we can now use predictive AI to scan through the chaotic libraries of nature. This approach allows scientists to find materials with ideal properties that were previously hidden within complex structures. It accelerates the pace of discovery from years to a matter of computational hours. So what happens now? The immediate goal for scientists is to replicate this meteoric material in the lab. The AI has provided the atomic blueprint. The challenge now is manufacturing. Researchers are working to create a lab-grown version in usable quantities, which would unlock its potential for real-world applications. Looking toward the near future, the first applications would likely be in aerospace. Imagine support structures for the next generation of space telescopes that are completely immune to thermal warping. This would allow for clearer images and more precise measurements of the cosmos. Components in high-powered electronics and quantum computers, which are extremely sensitive to temperature fluctuations, could also benefit immensely from this thermal stability. Further down the line, this opens up a new frontier of material science. Entire satellite frames or habitats on the Moon and Mars could be built from materials that are indifferent to extreme temperature swings. It also signals a new era of AI-driven prospecting. Future missions to asteroids might not just look for valuable metals, but for unique atomic structures with exotic properties that can only be found off-world and identified with artificial intelligence.
So the secret hidden inside that 300-year-old meteorite was an atomic recipe, a blueprint for a material that solves one of the oldest problems in engineering. This secret was unlocked by a new kind of intelligence that could see the hidden order within the chaos. This is just one example of how AI is becoming an essential partner in scientific discovery. Next time, we'll explore how another AI is helping astronomers decode the mysterious signals coming from the farthest reaches of the universe.